Hello everyone, welcome back to our channel Geomatics Engineering. Here we learn and explore the things related to geomatics engineering. So in this video we are going to talk about types of resolution. So if you are watching our channel first time, so subscribe it and also join the Telegram channel, link in the description. And to those people who are watching this video for resolution, first I will suggest them to go in the Telegram. There are some extras are available in PDF. Go read them and have an quite good information regarding some terms of remote sensing. So starting with our lecture, resolution. Resolution is defined as ability of sensor to differentiate between smaller differences in satellite image. Smaller differences in the satellite image. And the quantity of information and quality of information that a sensor records is depends upon the sensor's resolutions. There are four types of resolutions: spatial, spectral, radiometric, temporal. We will see each of them one by one. So starting with spatial resolution. Spatial resolution is defined as ability of sensor to differentiate between smallest possible object on ground. Means if a sensor is able to differentiate between a smaller and smaller object, it is said to be a good sensor and it having higher spatial resolution. We can also say that spatial resolution tell us about how much length and area of Earth's surface is covered by each pixel size and area respectively. Means pixel size is connected with the spatial resolution. The smaller the pixel size, the good is the resolution. Means if a pixel is representing small area on Earth, it is said to be a good resolution. Also, the number of pixels in an image is representing spatial resolution. For example, see this figure. In this figure, 60 by 60 meter land is represented. First, it is represented by one pixel. We cannot tell what is it showing. The whole land is represented by one color only. Then 30 by 30 pixels, 4 pixels are there. We can see the 4 different colors, but we are not able to differentiate between what is the information from the land is coming. Then again by increasing pixels and again increasing and again, when we have increased good amount of pixel around 3600 pixels and each pixel size is reduced up to 1 meter, we can see that there are several features, like here greeneries are also there, here some water bodies are also there, and also in between them there is a building, or we can say settlement also there. So we can differentiate between different features if our spatial resolution is good, or we can say number of pixels in the image is quite good amount. Again moving to further examples, here starting with D, our resolution is poor, 250 meter. We can have the image, but we cannot tell what different pixels are representing here. Again it is improved to 30 meter. The pixels are finer compared to previous one, but still we are not able to differentiate between the objects. In 10 meter resolution, we can differentiate the objects, that there are some linear features also. These are the linear features, and there are some also open area land. There are also some black areas. We can say that these are the water bodies or something. So we can differentiate between them. And when we will see in this image 1 meter resolution, we can even differentiate between these rotaries. We can see that there are some rotaries also. There are also lines between the lands also. We can see them too. So by improving the pixel size, by reducing their size, and by increasing number of pixels in an image, we can improve the spatial resolution. Again, there is another example. First, it is very coarser resolution. We cannot differentiate between buildings. Then it is a little finer resolution. We can see the building tops, different building tops. Again, this is more finer resolution and a very good resolution. We are even able to see the parked vehicles. So these are the resolutions, different resolution. It is also one example. Now, on which thing spatial resolution depends? It depends upon instant field of view, which is in short form IFOV. What is instant field of view? Instant field of view is the area on ground represented by each pixels, yeah, 1 pixel. Area of ground represented by 1 pixel, or we can say area of ground scanned in one click or a single step. So if this area on ground is large enough, or we can say very large, then spatial resolution is very poor. Means we can see the whole city in 1 pixel, but we are not able to differentiate between the features. If this area is less, or we can say 10 meter, one as we have seen in previous 1 meter, then we can say that our resolution is good. We can differentiate between several things. And this instant field of view depends upon two things, that is height of sensor, viewing angle of the sensor. If same sensor is placed at different height, then we must say that its area of view, instant field of view increases, and we will have poor resolution. Also, some sensors are able to tilt. If a sensor is viewing an area by just looking direct beneath it, or we can say it is also called as nadir view, then its resolution is good. It will look at a better resolution. But if it start off nadir viewing, off nadir viewing, then its resolution start decreasing. You can see nadir view and off nadir view in those PDF which are available on the Telegram. Now moving further, it is also example. Different instant field of view are there, and their resolution and their image are represented here. Have a look over it. Now spectral resolution. Spectral resolution is defined as ability of sensor to detect and differentiate between different wavelength of electromagnetic spectrum. We know that on our earth surface, different objects interact with electromagnetic spectrum in a different way. Some reflect some wavelengths, and some reflect some other wavelengths. So by detecting those wavelengths, we can differentiate between the features also. If a sensor is not able to differentiate between the different wavelength, it considered all the wavelength as a one, then it is not able to differentiate between the objects. So to have a proper differentiation and have a proper identification of objects, we need a good spectral resolution sensor which are able to differentiate between different wavelengths also. So these wavelengths are detected in the form of bands, and spatial resolution of sensor depends upon width of bands and number of bands. Now the width of bands define the range of wavelength captured by the sensor, and number of bands define the spectral resolution. For example, see here, there is a black and white film and color film. Black and white film consider the whole 0.4 micrometer to 0.7 micrometer wavelength, that is blue, green, red, in a one band only, and due to which we see the image black and white. There is no color in the image. So if someone wearing blue t-shirt and someone wearing red t-shirt, we will see only t-shirt only. In color film, if we can see that there are 3 bands, blue, green, red, separately, and their width are also narrow than this one. So now with blue object and green object and red object, we can have a different identification. We can see those objects separately. So it is a quite finer spectral resolution as compared to black and white film. Now it depends upon the width of resolution. Now let's see number of bands. It is depends upon width of the bands. Now we will see number of bands. Here single band is used. So all things are in a grayscale and single band is used. Single band means a range of wavelength is represented by a one band only. One band. And this band, the green color, blue color, violet color, all color are represented by a one band. So it is represented in a grayscale. It is also called panchromatic. Now multispectral. Multispectral means the whole electromagnetic region is covered in 4 to 8 bands. 4 to 8 bands. And their widths have different wavelengths, range of wavelengths. So we can see different features in different color and different identification we can apply. In hyperspectral, 100 or more than 100 bands are there. So their widths are narrower widths are there. But the problem is that in hyperspectral images, identification is good, but signal to noise ratio decreases. So we use less hyperspectral and use multispectral mode. It consists of 5 to 8 bands. Now moving further, we will see now radiometric resolution. Radiometric resolution is defined as ability of sensor to detect different values of electromagnetic energy. Means it tells us about the sensitivity of sensor towards electromagnetic energy, or we can say signal strength. Radiometric resolution is expressed in terms of bit values with base 2. For example, 2-bit radiometric resolution means each pixel can store 2 to the power 2. That means 4 different energy levels. These are also known as gray levels. These are also known as brightness levels. So depending upon this gray level or brightness level, we can say different electromagnetic energies can be stored in the pixels of the image. For example, here 2-bit, here 8-bit means we can have 256 different electromagnetic energy which can be stored in the pixels. Now let's see some examples. First, starting with the left one. Here 1-bit, that means only we are able to see 2 levels of electromagnetic energy. So one level is represented by black and another one is represented by white. That's only. Now moving to 2 bits, 4 levels are there, means 2 to the power 2. So we can see that there are some gray patches also, means we are able to detect 4 different electromagnetic energies. Now moving further, 4 bits, 16 levels are there, some extra shades are there. Now moving to 8-bit, 256 levels are there. So the image is more fine and we can easily differentiate between different objects. The grayscale improved, the gray level is increased. Here in 8-bit and 11-bit, what I was trying to show, that in 8-bit the shadow is there, shadow of cloud, and in this 11-bit shadow is there, but beneath the shadow some features are available. Means in 8-bit the electromagnetic energy of shadow everywhere is represented by same gray level, but in 11-bit different areas have different electromagnetic energy, and this it is able to differentiate between that also. So we are able to see the different object where shadows are light. So we are having good amount of discrimination in more radiometric resolutions. But as we are human, we have limitation in our eyes. Our eyes can view visually 40 to 50 shades of gray levels, 40 to 50 shades, but computers can detect all the gray levels. But experimentally it is seen that 8-bit is proved to be very good, but as we increase more radiometric resolution, again signal to noise ratio decreases. Now we have seen this term twice, signal to noise ratio. Let's see what is it mean. Signal to noise ratio is a measure to calculate amount of noise or hindrance available in the signal detected by sensor. It is basically a check which is required for checking the signal quality of signal detected. It is defined as the ratio of signal power to noise power, and the higher is the ratio, the less obstruction is there. So it means if ratio is decreases, that means noise power is increases and our signal is getting deteriorated. Now moving further to our last part, that is temporal resolution. Temporal resolution is defined as how frequently an area is imaged by a sensor repeatedly. It is used for change detection and analysis of parameter that varies with time. For example, IRS-1 have a sensor, IRS-1A sensor have temporal resolution 22 days. Temporal resolution means revisit period of the satellite, revisit period. Now don't confuse between revisit period and orbital period. Orbital period, both have different meaning. Orbital period is a time when satellite retraces its path, passing over the same point on the Earth with same inclination, or we can say direct beneath the satellite. Means if this land is being observed by a satellite with some angle, then this angle should be maintained, and then this land should be again retraced, then it is said to be a orbital period. Means the whole circle of the whole cycle of the sensor is completed. But revisit period is different than orbital period. There are some sensors which has ability to tilt their camera axis. They can tilt their camera axis, they can tilt. So it is possible for a sensor to have an image just by tilting their camera axis, then it can have an image of land more than once in its orbital periods. So revisit period for these type of sensors are less than orbital period. So don't get confused between revisit period and orbital period. There are some sensors, Spot, Landsat, NOAA, MODIS, and their temporal resolutions are there. So hope you have liked this video and understand the concepts. So if you have any queries, then mail us at our Gmail. Also join our Telegram channel. Share your experience in the comment box below. Thank you.